All right, this is page 123 of the note spiral, and we're still working with confidence intervals for means. And this is scenario 2. So you're going to want to have your recipe card available. So you probably want to have this open up so you can see the recipe. So a professor at a large university believes that students take an average of 15 credit hours per term. So he's saying, hey, their claim is 15. A random sample of 24 students in her class, so N equals 24, reported the following number of credit hours. Find a 95% confidence interval for the number of credit hours taken by the students in the professor's class, and then interpret the interval, and let's interpret the level. So first off, we need to define our parameters. Mu equals the true population mean number of credit hours. Now, some people are going to take more than 50. Some are going to take more. Some are going to take less. But we want the mean number of credit hours. So we're not worried about whether or not someone takes 10 hours. On average, how many are they taking? We're worried about the mean number of credit hours. So that's the first thing. We defined it. We did that. And the next thing we need to do is conditions. The first condition, random sample. It's almost always given. I've never seen it not. If it isn't given, you're going to say random sample is assumed. We're going to hope that they were smart enough to take a random sample. So random sample given, and they just happen to tell us, in this case, N equals 24. Number 2, N needs to be less than 10% of the population. 24 divided by 0.10, and it's always divided by 0.10, equals 240, which is less than 250. That's the population size, because they told us there are 250 students. So the sample size is less than 10% of the pop. All right, the next one, normality. Well, it's normal if they tell us the underlying distribution is normal. They weren't nice, so they didn't do that. So the next thing I'm hoping that I can check it by central limit theorem. Central limit theorem says if my sample size is 30 or larger, then I can say it's normal by central limit theorem, and I don't have a ton of work to do either. Well, it turns out they didn't do that either. So the next thing I do is I'm going to have to go ahead and check to see if it is by drawing a graph. The easiest graph to do is a box plot. So I've already entered this data into stat edit, and I entered all that data into column L1. All right. So once I've entered all that data into column L1, I'm going to second quit. I'm going to check your y equals, make sure there's nothing there. And then second stat plot, press enter, arrow to the left to make sure it's on, drop down and select the one that has the outliers, the one with the dots. I stored this data in L1, so second 1. My frequency needs to be 1. And then I press zoom 9. And what I get is a nice box plot that doesn't have any outliers. All right. So what I'm looking for is something that's reasonably symmetric, and there's a lot of times their graphs don't look that symmetric, say that they are, but also note that there's no outliers. If you come up with an outlier, chances are you have a data entry error, so because you can't proceed if you do. So check and re-enter that if you have a really ugly graph. All right, so I'm going to go ahead and draw this, and I'm just going to sketch it based on the way it looked on my, and that's about what it looked like. I can go back and use the trace button, and it'll give me each value. So my lower value, my scale right here is going to be 12 all the way to 21. So this is 12, this is 21. Turns out this was at 15, this was at 16.5, and this was at 18. And by the way, you don't have to draw a complete scale if you label things. So if you want to draw a complete scale, you can. Or if you just want to label it out like that, that's fine as well. Now, when just drawing a graph is not enough. So the box plot is reasonably symmetric. This one's pretty symmetric with no outliers. Okay. The distribution appears to be approximately normal or reasonably normal. You want to always put some sort of qualifier in there. All right, so we checked it. Now, we need to go ahead and write the equation. Our equation is x bar plus or minus t star s divided by square root of n. Well, unfortunately, they didn't give us x bar, they didn't give us t star, they didn't give us s, they didn't give us the square root of n. But this has been a long time, but if we go back and go stat, calc, one variable statistics, my list was L1, and I get an x bar, and I highly recommend writing this off to the side. X bar equals 16.625, S equals 2.222, N we know is 24. Also, our degrees of freedom is 24 minus 1. And we need to calculate T star. So let's go back and calculate T star. So second vars, inverse T, parenthesis 1 minus 0.90, close parenthesis, divided by, oh, excuse me, not 90, it's supposed to be a 95%. Divided by 2, because what we're doing, we're looking for a lower and an upper with centered at 0.95. Degrees of freedom are going to be 24 minus 1, or you could just type in 23. And I end up getting a T star of 2.0686. So I can plug into the equation, and I'm going to have 16.625 plus or minus 2.0686, and S is 2.222 divided by the square root of 24. Stat test, drop down to number 8. Now we actually entered data. Now all that stuff they actually brought over, okay? So I could just go to data if I wanted to. Data, my list was L1. I want to make 0.95 confidence level. And once again, it gives me my X bar, it gives me my S, it gives me my N. So there's a shortcut there if you'd like to take it. I'll let you figure out what it was. And there you go. All right. Next thing, we have to write our conclusion. We are 95% confident that the true population mean number of credit hours lies within the interval 15.686, and 17.564. All right. And once again, true population mean number of credit hours, true population mean number of credit hours that came from up there. There's our confidence level, there's our interval. So basically, we really are just taking what we found. Now we need to interpret the confidence level. So now we need to interpret the confidence level. And that's number 12. In repeated sampling. So in other words, if I did this over a bunch of times, we expect this method to capture the true population mean number of credit hours 95% of the time. Once again, here you are just telling them how great you are. Our thing works 95%. If we did this a bunch of times, if we did it a million times, it works 95% of the time. We're also saying it doesn't work 95% of the time. Our interval that we calculated above was 15.686 to 17.564. And we have one last question. Does the sample indicate that students are taking more credit hours than the professor believes? Because, and the answer is yes. Because the interval does not contain 15 and it lies above 15, we believe the students are taking more than 15 credit hours. All right. Because the interval does not contain 15 and it lies above 15, we believe the students are taking more than 15 credit hours. Perfect. What about this? What if it had just been this? 14.99999 to 24.0. Well, guess what? Because 15 lies within that interval, we couldn't say the professor was wrong. All right. So if it contains it, we can't disagree with it. But if it doesn't, we can make a statement about it. So that includes page 123. I highly recommend you try out page 124 on your own and make sure that you're able to do that.